Good morning. Today we are going to talk about the lower region of blast furnace, where primarily we will see Bosch, belly, and lower stack. Out of all these three segments, we must be knowing that all these three segments are exposed to severe heat load. And for example, in extreme right segment of the slide, it has very clearly shown that total heat load sharing is more than 50% in this region. So we can say that this is one of the most important reasons. And the same outcome is being addressed in a figure of heat load where primarily two conditions has been chosen, a, a skull setup and when there is a peeling of skull. So in both setup, it is shown that in a case when there is no skull, heat load rises tremendously. And in this context of severe heat load bearing capacity of Bosch belly and lower stack, the design of Bosch become very important. And design constitute primarily of the Bosch angle. So let us have our next slide where we can just elaborate on this Bosch angle. As we can see our extreme left hand side, this is the new furnace where Bosch angle is uh, uh, minimal. And why we say minimal? Because as soon as the due course of time, we start running the furnace with a ramping up. At that time, this boss angle keep on increasing. And as the subsequent diagrams after years of operation, it has very clearly shown. What exactly it means? As Bosch angle keep on increasing, the material sliding on the surface of the boss area tremendously gets increased due to this increase in Bosch angle. At the same time, our jetting of the uh, outcoming gases from the raceway also change its profile in this region. So we can say that with the change in angle, the feeding rate from the cohesive zone through the dripping area gets tremendously increased on this Bosch incline. And at the same time, if this Bosch area is not backed up by a good cooling system, or if any damage found in this region, then this create a big problem in this region. And it's really very difficult to run the furnace. Similarly, when the Bosch angle is too low, at that moment, our gas jetting will be tremendously increased. At the same time, the feeding rate for the cohesive zone to dripping is also throttled. Uh, so this angle keep on really contributing to the production of the furnaces magnificently. So we can say that a very high productive furnace, this Bosch angle is bit higher so that we can feed fastly uh, on a downward region. At the same time, we have a more volume of uh, pause to accommodate a pause gases. generated from raceway. So this is all about the angles and the area of the Bosch, which is supplemented by good cooling and refractory system. Because once cooling system damages, it damages the refractory, and once it damages the refractory, then Bosch angle goes on increasing. And once Bosch angle goes on increasing, our feeding rate to the raceway will be different than what designer has designed for production and productivity. So now coming to the actual area where this boss angle gets changed due to damage of refractory, and damage of refractory is basically due to damage of the cooling system, because we all know that cooling system of any furnaces is composed of refractory and copper coolers. 95% of the total heat load is being carried out by cooling system of the copper system, or we can say copper system staves, and 5% of the heat is only carried out by the shell. So in the process, if coolers gets damaged, really the total heat cannot be come out with the shell, and that is the reason our refractory gets overheating and its life gets decreased. And once this life gets decreased, then there is a washing of this refractory. At the same time, then our exposure to the copper coolers becomes naked, and its damages accelerated several fold due to absence of these refractories. At the same time, due to absence of this cooling system, the crust which formed to take care of the cooling system as a protective layer also peel off. And once it's peel off, the copper coolers are exposed to severe heat load. And as you must be knowing, copper conductivity is pretty good, but once it is more than 200, the grain boundaries start uh, showing a, deformations. And as we must be knowing, its shafting temperature is around 700, and more than that, everything is going well. And these cooling systems, the reasons it procured, it fixed, it works of a very high temperature region. So we know that in this reason it gets damaged in absence of water or cooling system failure. At the same time, there are continuous peeling of this slack rust which form on the copper shifts are also are the reasons of damaging these coolers. Now coming to the different type of damages are a sort of backfill, or we can say that sometime when the motor in between these coolers and shell lost, and when coolers gets a, a atmosphere of heat load, then there is a stress and strain form, and this takes a shape of banana, and this is called banana effect. And due to this, there is a curvature form in the stiffs, and that becomes a source point of damage creation in the stiffs. Now, as we must be knowing that hydrogen diseases are also a killing effect on the mm, mm, this damage phenomena. So we can say that mechanical wear, banana effect, hydrogen diseases, and oxygen content, all these are really very detrimental for copper coolers in the lower region. And it's really amazingly needed to take care in all these area so that these all copper coolers can be preserved well. By doing so, refractory can be kept intact in this region, and once refractory kept intact in this region, copper coolers can be taken care in better way. And for a long time, we could able to produce from the furnace for a longer period and without interruption. And in that way, we can produce low cost hot metal and which has a alignment with the organization objective too. Thank you.